Check it out now, y'all.
nanoHUB-U, online instruction.
Hi everybody, this is nanoHUB-U, lecture 2.2, and we'll be going over how wave optics can be treated using a transfer matrix approach, much like we did ray optics in lecture 2.1. So here's kind of a general sense of how these wave optic-based transfer matrix methods work. So we kind of know already how to calculate what happens at a single interface if we have two semi-infinite regions. And so in particular, we have at normal incidence Fresnel's equations are given by the following expression. So basically the difference of the refractive indices between two media divided by their sum, and then that quantity squared. And then of course, if it's non-absorbing media, then transmission must be 1 minus the reflection. And so you can kind of see here schematically what's happening. So we have like basically an incident wave from above, which we call D1 because it's going down. And then we have another incident wave from below that's going up, so we call it U0. And then the indices, upper indices are associated with which layer you're in. And then the letter up or down just tells you is the wave going up or down, not where it's come from, but where it's going to. Okay, and so the thing that's interesting is once you have that framework established, then the only other missing piece is that you have to include the phases as you propagate through the different layers. So depending on like where the phase offsets are occurring, then you can basically introduce like a phase of either e to the plus or minus j times the propagation vector in that direction, beta times z. So that's kind of like a single component of the overall wave vector k. And so then you can create an expression for the overall output in the up direction, du1, which is a superposition of the transmission of u naught times the phase factor, and then the transmission in the down direction times the reflection times another phase factor. And then for the down component, of course, it will be basically fed in by the same two sets of matrix elements. But of course, U naught is transmitted back, or sorry, reflected back. And so then that gives us an R. And then we have transmission from D1 to D0 T. Okay? And so remember, we were talking about U and D. Another way that we could write it would be E plus and E minus. But what's interesting is like there's another way we could write in terms of E fields and B fields instead of E plus and E minus. And that's actually equivalent to what we were doing earlier. So if we take into account basically Faraday's equations in order to construct the total E field in terms of E plus and E minus, as well as the total B field in terms of E plus and E minus, then we can get the E field not only like at kind of the beginning of the range of the layer, but also at the end at a position L. And then we can write that exclusively in terms of the initial E and B fields plus the phase factors. And so then that ends up looking like this, where we have E of L is going to be 1/2 times this E plus term times this phase factor, e to the j beta L, then 1/2 times the E minus term, which is E naught plus C over N B naught times e to the minus j beta L. So then we can kind of summarize those contributions using like sums and differences of the complex exponentials as sines and cosines. And so that allows us to write a transfer matrix for E and B fields in terms of elementary trigonometric functions, which look like cosine beta L and minus n over c, or minus c over n times sine beta L. Okay. So once we have things represented in that format, we notice a couple things. Clearly, there's a big difference from what we had before, because even if we're propagating through free space, we actually pick up complex phase factors. So why didn't we see that earlier? So the reason is very simple, actually, which is that, first of all, the representation is different because we're doing E and B fields instead of height and angle, right? So that's immediately a big difference. But the second difference is that in the ray optics picture, we pretty much ignored phase, but now phase is coming to the forefront with these sine and cosine functions. And so as long as the number of cycles is fairly limited, in other words, beta L is on the order of, say, several times 2 pi or less for plausible lengths in the system, then you can expect that the phase factors will make a big difference. On the other hand, if beta L was extremely large, like let's say it was 10 million, then the interference peaks are going to be so close together because beta is proportional to frequency that you won't even be able to notice the impact of the phase variation, and therefore you could kind of simplify it back to the original ray optics picture. But again, just like what we had in ray optics, we have these 2x2 linear matrices as before, and we can also take matrix products and compose them together. Oops, sorry. So basically we have like the possibility of looking at propagation through multiple layers. And the point is that we start off with these layers, U0 and D0, okay? And basically we want to be able to propagate through up to n layers. And so using kind of that framework that we had earlier for just a single interface between layers 0 and 1, then we can kind of extend that to like a much larger number of matrices. Now, of course, we could also represent it in a different way, looking at the total E fields and B fields, which we could also label as U and V. And so that's like another way that we can label it. Also, like another way to think about it is that we have two different polarizations within each layer. And so that's kind of an orthogonal but equivalent representation. And so we have those options. So now we're going to talk a little more detail about how do we construct these wave matrices in the case of U and D. So up and down. So this is like kind of moving away from the E and B fields to be more general. So if we have, like say P layers, and then we want to add the P plus 1th layer, so this will be almost like a proof by induction, then we have to do two things. Okay, so first of all, we have to set up a pair of so-called W matrices. And then we multiply these W matrices times the U and D fields in our system. Okay, and so then the product of those two things has to be equal right at the boundary. And then second, we actually have to have what we call layer T-matrix. And that layer T-matrix will basically allow us to transition between the Pth layer, which we have already solved by assumption, and then the P plus 1th layer that we're trying to solve. And now we're going to actually write the layer T-matrix as a product of two terms. And so we call them Tp and then phi p. And then Tp is the interface T-matrix. And so that basically has to be the quotient of those two W functions that we had before right at the boundary by definition. So in other words, what that tells us is that the fields have to have like kind of a fixed relationship with one another at the boundaries that depend on the properties of both the P and P plus 1th layer. And then we have the propagation matrix. And then this propagation matrix, phi p, which we talked about earlier, is going to be very similar to those two phase factors I talked about earlier, the E plus or minus J beta L, except in this case we write a more general like beta M plus in layer P and then a beta M minus in layer P. And so usually those would be equal and opposite in value, but maybe not always. And then L could be generalized to a delta YP so we can keep track of multiple thicknesses. Okay, so just to give you a very simple example, let's say that we have a whole bunch of very thin layers, which are a quarter wavelength in optical wavelength space. Okay, so actually, like, because the phase factor becomes pi over 2, then all the cosine terms become 0, and then all the sine terms become maximum. And so then we are left exclusively with off-diagonal elements for both layers, the high and low index media. And then we multiply those together, then we actually get something that is on diagonal. Okay, so basically what's happened is we are picking up like an overall phase factor that's kind of like a multiple of 2 pi. And so then we end up with this relationship after one full period that EA and BA are equal to N1 over N2 or N2 over N1 times our original E naught and B naught. So then if we compose all these matrices together in a periodic system, much like we did last time, then we get that the overall transmission of the system would be like the N1 over N2 to the 2m exponent, right? Where m is like the total number of bilayers in the system. Okay, so then that allows us to predict that a quarter wave stack would be very good at attenuating light. Okay, so in other words, it would be a very strong reflector at or near the wavelengths where each layer is a quarter of the optical wavelength. Okay, but you can obviously see from the phase sensitivity that if you try to double the frequency, then it would behave much differently. So it's not actually going to work at every possible wavelength, but just a selected range of wavelengths. And so that actually like kind of links in with our band structure analysis before, where we said that if we have certain specific values of the frequency or the wave vector, then we'll have forbidden modes, and otherwise we can have propagating modes like in free space, right? And so this is kind of an example of a 1D photonic band gap, like at that quarter wave condition. Okay, so it's clear that there's a mathematical problem with the way that these things are constructed though. So in case you didn't notice, the diagonal elements were kind of like the the multiplicative inverses of one another. So one was N1 over N2, other was N2 over N1 to the 2mth power. So that means that one of them is going to become extremely large as we increase the number of periods. So that might sound like, okay, that's not a big problem, we can deal with that analytically. But if you put that into a computer, there are really finite limits on how large you can allow the values to be. So if you don't deal with that intelligently in advance, then of course you're going to have numerical overflows and you're going to have large errors in terms of predicting the overall transmission and reflection of the system. So it's really important that we actually reformulate the transfer matrix approach, where we just go from the first layer to the second layer to the third layer to the fourth layer in a more numerically stable fashion. And the two approaches that can be taken are called the R-Matrix and the S-Matrix approaches. Now, I'm not going to cover the R-Matrix in a great deal of detail because we're not really going to use it, but essentially it connects polarizations on both sides to the other polarizations on both sides. And so you can kind of think of this R matrix as the field impedance of your structure. Now the S-Matrices, which we will be covering in great detail, cover both incoming and outgoing fields from boundary regions. Okay, and so the reason we want to do that is actually very physical. So that goes back to the very beginning of this lecture, in which we talked about like what happens when you just have like an interface between two media. And we said that we can look at the transmission and reflection of both incoming beams, and then that gives us the two outgoing beams. And so now what we're going to say is we want to actually formalize that system. So instead of trying to look at just one layer at a time, we actually look at kind of inputs, and then we look at outputs. And then there's a very good physical reason. So first of all, we can understand very logically like that all the matrix elements associated with this formulation will correspond to a physical transmission or reflection. So that's like a very straightforward interpretation of these matrix elements is in fact the most clear physical picture of the system. And then second, something very important is that we know for any kind of normal system that's not a gain medium, then the transmission reflection should be bounded between 0 and 1. So then that means that we're always going to have something that should be numerically stable as long as we calculate it in the proper fashion. And so in particular, you can see that like if you look at this matrix element, then we have like that the upper output would be equal to transmission in the up direction of the beam in layer 0. Okay, so then we call that T-U-U through P layers. And then similarly, in order to get the overall reflection in the up direction in the P+1 layer, we take the RPUD of dP+1. So basically that's like a reflection at the top of the structure. And then similarly, we can do something like to get the total output going in the down direction, the D0. Okay, so S-Matrices have like a number of nice properties that we want to use. And so in particular, they're unitary, which means that if we take the adjoint of the S-matrix and then multiply it by itself, then we always recover the unit matrix. And so in case you're not familiar with the adjoint, that would be essentially the transpose times the complex conjugate of the S-matrix. And of course, if S-matrices are pure real, then that means that the transpose of S times S would be equal to 1. And like I said before, there's no exponentially growing terms. All the exponentials are actually going to be in the denominator of the system. And then third, and most importantly, this will be much more numerically stable than the T-matrix approach, in which we just treat each layer one by one, going all the way through the system. So now we're going to talk briefly about how do we construct the S-matrices. Okay, so there are different ways to do this, of course. So the most obvious way is essentially if we already have a T-matrix that we calculated between the 0th and P+1th layer, then we can basically rewrite the equations so that everything would be calculated in terms of the up output in the P+1 layer, UP+1, and then in terms of D0, okay? And so you can see like that we just did the calculation here where we kind of expanded the original T-matrix terms, and then we rewrote this in terms of D0 and UP+1. And then we basically end up with these two terms. And of course, again, it has to be linear in terms of the two inputs, which are now considered to be U0 and then P+1. Okay, and so then we end up with this matrix in which basically we have the upper left-hand term for the transmission would be A minus BC over D. The reflection would be B over D. And then the reflection in the other direction would be minus C over D. And then finally, a transmission in the down direction of 1 over D. Okay, and so then we want to talk about like how are we going to construct the overall S matrix. So we just want to use an analogy with the approach that we had before for the T matrix and define an S layer matrix. And again, the S layer matrix essentially connects what's happening in the inputs and the outputs, much like we connected the two layers before in the T matrix. And we can actually write this S layer matrix as a product of three terms, which are simpler. So one would be propagation through the one layer, like in the minus direction for the down direction. Okay, and so then that's this first term. And so of course we just have one entry now that's differing from the identity matrix. Then we multiply by the S layer matrix, which we'll explain in a minute. And then we have this phase factor here. And then this phase factor only differs from unity in the upper left-hand corner. So you can see that when you compose these together, if the S layer matrix is trivial, if it's unity, then we recover that phi p that we had earlier with the T matrix. Now we can try to actually relate the S matrix to the T matrix like more explicitly. And that allows us to actually devise like an iterative formulation of the S-matrices, in which basically we engage in the same kind of calculation that we had earlier, but we kind of recycle like a lot of the T and R matrices from the P minus 1th layer in order to get the Pth S matrix. Okay, so the idea is we basically will build up the S matrix step by step as we add more layers. And of course it starts off as like pretty trivial, like essentially like the T matrix, which would be between two layers, or like a S matrix like we explicitly constructed in the first slide of this presentation. But then it becomes more and more complicated over time. And you can see the 4 entries are listed here in detail. So if you wanted to implement that yourself, you can do it. Now, of course, we haven't gone through all the details of even what an S matrix is, much less how to use it. So we'll be covering that more in the next class. Thank you.